So this synthetic map is a lot of things to keep track of, and this is far from complete. None of these steps involves changes to the carbon-carbon skeleton, and one thing we want to be able to do with synthesis is to increase not only the number of carbons we have, but also the degree of substitution. To add that functionality, we include Grignard reagents. And our Grignard reactions are going to perform nucleophilic attack on the carbonyl carbon. So when we think of synthesis, we want to think of starting from something simple, like an alkane with a few carbons in it, to making something much more complex. So we'll do some radical halogenation, then we'll change to an alcohol, we'll oxidize it, get a ketone or an aldehyde, and then we'll do a Grignard reaction with that. And let's just quickly review the mechanics of a Grignard reaction. Don't forget, our Grignard reagents take the form of alkyl magnesium halides, like methyl magnesium bromate, CH3MgBr. To make a Grignard reagent, you just take an alkyl halide and you react it with magnesium in diethyl ether. And that makes our Grignard reagent. So in the first step of our Grignard reaction, the Grignard reagent acts as a carbanion. Right, so methyl magnesium bromide, it's like a methide ion and a magnesium bromide cation. And the first step is nucleophilic attack, which exceeds the octet on the carbonyl, to make an oxyanion. So there's our oxyanion, and here's the methyl group that we added, and then water is the weak acid that protonates it. And so that's a Grignard on a ketone. We can do it on an aldehyde as well to make a secondary alcohol. And finally, if you use excess Grignard on an ester, you end up with a tertiary alcohol. So what's the mechanism of that? So here we're going to take the ester named methyl butanoate, and we're going to react it with excess methyl magnesium bromide, that's our Grignard, followed by water, and we're going to end up with 2-methyl-2-pentanol and methanol. The methanol actually comes from that methoxy group in the initial ester. Let's look at the mechanism. In our first step, which is nucleophilic attack, the carbanion of the Grignard attacks at the carbonyl carbon, which exceeds its octet, changing this pi bond into a lone pair. The second step here is loss of a leaving group. When the carbonyl pi bond reforms and a methoxide leaves. So here's that methoxide that we kicked off. Right, that methoxide is going to become the methanol when we protonate with water. And our product now is 2-pentanone. Now we're going to do our second nucleophilic attack. So this step looks very much like the first step, where our methyl magnesium bromide, another equivalent, this is why we needed excess, there's nucleophilic attack at the carbonyl carbon. This exceeds the octet here, and so we have to change a pi bond to a lone pair. And now we've made this tertiary alkoxide. And now all we need to do is protonate it. And of course, we're going to use water to do that. So, the alkoxide acts as a base, it attacks the proton, and that sigma bond turns into a lone pair. And this is our final step, proton transfer. So now that we've reviewed some Grignard reactions, you try one. What will be the product when we react this 2,5-dimethylcyclohexanone with the Grignard reagent ethyl magnesium bromide, followed by a little bit of acid. Pause your video and work it out. When you've got the answer, then you can unpause it. Here's the solution. This is the ethyl group from our ethyl magnesium bromide. This pair of electrons, this nucleophilic attack at the carbonyl carbon, that exceeds the octet there, so it changes into a lone pair, pi bond to lone pair. This bond right here came from this lone pair of electrons. And you can see that is the ethyl group that we added. And of course, this is an oxyanion. With a negative charge. And now we use a little bit of acid to protonate it, but we don't even need acid, we could just use water here. So, proton transfer. And there is our final product.